Hello. Let us go through a quick introduction to DC circuits. Okay, so first of all, the objectives are to understand the importance of applying units. So we're going to learn or review scientific units. And because of the results of units of measurement, we can ensure that the numerical values we obtain through the equations are consistent. Also, we want to become familiar with the SI system, or the SI system of units, because we know that we have the imperial system of units and the SI system. And this is used through electrical and electronics theory and industry a lot. So we're going to be reviewing the system of SI is the International System of Units. Also, we want to understand the importance of powers of 10 and how to properly name our units, such as milli, kilo, etc. And we want to be able to convert any quantity into any system of units from different systems. Okay, so in other words, we want to be able to convert feet to meters, etc. A brief history. So if we go all the way to after death of Christ, zero after death, we will have that, it's not shown here, but Romans found, and Greeks before Christ too, found rocks in different islands throughout Greece and throughout Italy, that they called magneta, and they call them magneta because they came from a place, the island was called magneta, and those rocks had properties where they could attract metals and different types of conducting materials. Of course, back then they didn't understand very well conducting materials, but they did know that there were properties that they couldn't understand very well, and that was fascinating. But if we go forward all the way to 1400s, 1500s, 1600s, and 1700s, we have people like Michael Faraday, and Faraday did a lot of experiments with electromagnetism for capacitance, for magnetic inductance, etc. We had Lord Bacon, who actually used the first time term electricity, which comes from Greek. It means electra means ember, and it's because back then they were rubbing pieces of glass with ember, and they were able to create static charges on the piece of rod, a glass rod. Okay, but if we go to the interesting part at 1900, we have the vacuum tube, which was old amplifiers and old TVs. So this was for TVs. And we have radios. So we have AM radio and FM radio. AM radio was first, and then we have FM radio. Um, okay, then we have broadcast of television. We have color TV in 1940s, but this is really Europe. We have first mobile phone in 1946, and this was because of all the research done through the war. Um, a lot of these things were because of the World War. Then we have electric computers, first concepts in 1945. We have the solid state era, where you can save things, and we have memory devices in 1947. We have floppy disks, which I don't know if you've seen. I think I have one here. Yeah, floppy disks like this. I'm sure you've seen them at least in movies. So floppy disks were invented and used from 1970 and up. Then we have the Apple's mouse. The mouse is a very cool technology because it requires communication with the server, with the system. A floppy disk is a memory device to save information. Then we have first laptop in 1979 in the US. First assembled PC. from Apple in 1979, 77. Then we have the cell phone, really for everybody, not just for military purpose, and it's 1991. We have the first iPhone in 2007. That was iPhone 3, if I'm not mistaken. We have the man wrister, which is a very cool technology we'll talk about later in a few weeks. And we started researching, the scientific community started researching nanotechnology. Also in 1996, we have the Wi-Fi developments. iPod is in 2001. The Pentium 4, the chip for uh, RAM is shows up in 2001, and it has 1.5 gigahertz, which is huge velocity, huge speed back then. Then we have an Intel Core 2. Right now we're Intel Core 7. Right now they have the Core 2. We have has 3 gigahertz, and this was 2006. iPad came out at 2010. Electric car, the Volt from Chevy, came out in 2011. iPhone 6X came out in 2014. Fuel cell car, this one right here for hybrid cars, came out in 2014. And etc. We have the Samsung Galaxy and etc. So a lot of things from here on out, from this region out, have one thing in common, and is they use a lot of transistors, which we'll briefly talk about later. And transistors, as you know, have the property of being electronic gates. And part of the introduction, I guess, could be that in electrical and electronic engineering, you have two main fields: passive elements and active elements. Passive elements are resistors, capacitors, inductors. Resistors have units of ohms, capacitors have units of Faraday, and inductors have units of, sorry, inductors, this is not an inductor. Inductor is more like a coil. And inductors have units of henries. So the unit is henries, the sign, the symbol is like a coil. We'll talk about this later. These three elements, resistors, capacitors, and inductors, are passive elements. And they're used throughout for filters, for voltage dividers, for a lot of things. Active elements are transistors, amplifiers, and mostly diodes. Diodes are passive elements. Diodes are passive elements. But mostly transistors and amplifiers are active elements. And there are a bunch of different types of transistors and a bunch of different types of amplifiers. So transistors and amplifiers are used in electronics because they can allow the usage that you can design flip-flops, and you can design digital technology where a combination of digital uh, a combination of transistors can create a digital gate where you can save information, where you can pass um, one value versus the other, etc. So the smaller the transistor, the obviously you can assemble more transistors in a small area. For instance, this little processor, the Core 7 Intel, is basically the size of a stamp, holds 1.4 million transistors to be able to operate, to be able to compute all the computations that you have to do in the speed, which the speed, I don't know, I say up to 5 gigahertz, I forget the speed, but this is based on the clock, right? The crystal, which is a clock, and the clock will determine how many operations per minute per second can be done. But anyway, so that's part of the history that we want to talk about. We'll talk about more history once we start seeing more components. But in general, I want to introduce the concept of engineering system and engineering applications. So science and engineering are divided in basically three main regions. The mathematical foundations, which is what you learn in college and in university. So college, university, you learn all the mathematical foundations and all the physical theory and all the chemical relationship and all the material science. So for instance, in this particular case for electronics, you have network theory, you have logic theory, which is digital systems and transistors and flip-flops. You have system theory, which is all the free body, free body diagram and all the thermodynamic conditions and all the Ohm's law and everything. Then you have the physical conditions, which is reality, which you do by experiments, okay, by tests, and this is both in industry and in academia, so university and college. So physical foundations are the electromagnetics, the solid state physics, optics. You can also add more stuff here. You can add dielectrics, etc. And then you have the applications. This is what basically we go for industry or research. So what you learn in school and what you learn or apply in industry can also be used for developing new industry, new research and new applications in industry. So the applications could be power systems, kind of like power grid or transmissions, anything that takes form of power to perform energy. Electric machinery, so pumps, compressors, electric motors, combustion engines. Analog electronics, so we have some types of sensors, we have signal conditioners. Digital electronics, so we have flip-flops, we have logic gates, we have counters. Computer systems, which we have all the software and all the hardware for computers. Control systems, which is huge because we have all the instrumentation and all the sensor and actuator for mostly every industry. Communication systems, which is also a piece of a huge field right now, which is could be optics, optic communication, or telecommunication, or radio communication, etc. And instrumentation system, which is very, very, very closely related to controls. The difference is the instrumentation is the hardware, so it's the actual sensor going into an engine, the temperature, the pressure, the flow rate, versus the control system is the software, which you wrote a code to control those variables and allow more mass flow of gas and control the threshold temperature, etc. So the software does the controlling, the hardware is the instrumentation. So for instance, we were talking about a car, and a car has a lot of the systems that subsystems that could be a good example to start the introduction for electronics. So you have the body or chassis of the car, you have the body, we're talking about subsystems. You have the vehicle control, you have the powertrain, the transmission, etc. You have the instrumentation, which is all the sensors and actuators. And a lot of cars now have entertainment, which is a huge deal because many people buy cars based on what features they have for this particular section. Not so much about the powertrain and the instrumentation and the control, but a lot of people buy it based on instrumentation. Sorry, in entertainment. So the first one is electronics, the body electronics. So we have airbags. Do you know how airbags work? They're basically a nanosecond explosion. We'll talk about nanoseconds later. So when there's an impact, there's a triggering device which causes an explosion, and that explosion will inflate the bag. This happens in nanoseconds, which is 10 to the negative 9 seconds. We will see how to get to this number if you haven't seen engineering notation. This is basically 0 0.1, 2, 3, 4, 5, 6, 7, 8, 9. So, in this amount of seconds, this is very small time. In this amount of seconds, an explosion happens and the bags inflate. Okay, so a lot of systems that we deal with have explosions to operate. Airbags is one of them. The climate control, so this is the AC, the heater, the security, so the keys, the security is the locking and opening. The sensors to let you know that you have not you haven't used your seatbelt. Memory seat to go back to the features that you had. The mirror that you can fix from a button. The multiplexing to be able to play different stations or different things at different parts of the radio of the car. Now the control, we have the anti-lock brake. We have traction control. Some cars have suspension control, kind of like the Land Rover. Power settings, if we want four-wheel drive or only two-wheel drive. There you go, the four-wheel steer. So like the G-Wagon can automatically detect what tire needs more torque. Tire pressure sensor. What about the powertrain? We have the engine, which could be combustion by gas or diesel. We have the transmission, which could be mechanical or automatic. We have charging if it's a electric car. The cruise control, which is just a button to let the car know that you want to maintain the velocity. The cooling fan, so this is the fan to let your radiator extract heat from the engine. The ignition, which if it's a combustion engine with gas, it will be a current to the starter and the starter creating a spark from the spark plug, and then the explosion will start the movement of the pistons up and down. So this is the piston and it will start moving up and down based on the ignition. If it's diesel, you don't have the spark plug, you will have a huge air pressure, and diesel won't need that spark. For that, it will be just based on so much pressure that it will start combustion by itself. The four-wheel drive, now you only need a button to choose what full-wheel drive option you want. What about instrumentation? The instrumentation, we have the analog dash, kind of like the to tell you the speed, because we'll see the difference between analog and digital again. The digital, which is kind of like the value of temperature or value of or the radio station is digital. The navigation, which is the maps. The entertainment, which we talked about earlier, so able to connect to your phone, what the music that you want to play, the radio stations, is it digital radio, if you can play movies, etc. So these are common parts for modern cars. All right, so as we said before, we want to learn about units of measurement for SI system. So these are mostly for electric field. So we won't have a lot of we won't have for thermodynamic, you have entropy and you have enthalpy. We won't have those here. We can talk about them later if we have an example, but for now we just want to focus on the units that we will use throughout this class. So capacitance has the letter capital C. It has units of farad, and it's a capital F, the unit. Charge, electric charge, has the unit of Coulomb, Q, and has the unit of capital C. So capacitance is capital F, charge is capital C. The unit, the variable is capacitance C, charge is Q, but please don't confuse the unit with the symbol, with the variable. So if they tell you a capacitor has 0.1 microfarad, you'll see this on a capacitor that will tell you 0.1 microfarad. So it won't say C anywhere. Well, maybe you'll see it when you buy it, but you have to know that the units of capacitance um, and the symbol are very important to remember. Okay, so the units, I'm actually thinking that this is a mistake. This should be here and this should be here. Okay, so in other words, you have capacitance, you have charge, you have conductance, which is G, not C. You have energy, which is W, sometimes also E, depending if the system is giving energy or if the system is receiving energy. Frequency is lowercase f. Impedance is capital Z. This is for AC. Inductance is for magnetic properties. This is capital L. Power is capital P. Reactance is X, capital X, but this is for AC circuit. We won't talk about that too much. Resistance is R, capital R, and voltage is capital V. Okay, so the SI unit is Coulomb for charge, conductance is Siemens, energy is joules, frequency is hertz, impedance is ohms, Henry is inductance, power is watts, reactance is also ohms, resistance is also ohms, and voltage is volts. And the abbreviation in Siemens is S, joules is J, hertz is HZ, ohms is omega, Henry's is capital H, watt is capital W, ohms is omega, and volts is V, capital V. The prefix is very important. So we have gigahertz, kind of like for a processor, and it's 10 to the 9 hertz. So this is 10 to the 9 hertz. And if they tell you, sorry, and if they say kilohertz, for instance, so we already said kilohertz, so kilo ohms is 10 to the 3 ohms, or let's say 3 kilo ohms is 3 times 10 to the 3 is 1,000, so 3,000 ohms, etc. So very important that we learn the scientific notation. Giga is 10 to the 9, kilo is 10 to the 3. We're missing between 10, a common one between 10 to the 3 and 10 to the 9 is mega, which is 10 to the 6. So in here we should have 10 to the 6, which is mega, a capital M. We have deci, which is 10 to the negative 1, so decimal, etc. We have centimeters, which is 10 to the negative 2. We have milli, like millimeters, 10 to the negative 3. 10 to the negative 2 is, so 10 to the negative 2 equals 0.01. 10 to the negative 3 is 0.001. And you keep getting smaller with when you have a smaller number on top. So a power, negative 6 is obviously smaller than negative 3, so this number will be much smaller than milli. Micro, which is a mu, Greek letter, is 10 to the negative 6. Nano, which is a lowercase n, is 10 to the negative 9 nanometers. Pico is extremely small, is 10 to the negative 12. Yeah, 10 to the negative 12, that's correct. So, for instance, 1,000 is 10 to the 3, we said this, kilo. 100 is 10 to the 2. 10 is 10 to the 1. And 1 is 10 to the 0. This is important to remember. If you don't remember this, you can always use a calculator. So comparing units. We compare units when we have different systems of units. So for instance, if we have meters versus feet, or versus miles, So we know that 1 mile is 11600 meters, I think. Yeah, so yeah, 1 mile is 1600 meters or 1.6 kilometers. So when we compare units, we need to know what is the basic rate of change. And this is always the same. It's not like if you exchange dollars for euros that it will be one price today, but it will be a different price next week. No, these will always be like this. If you remember a few, it's good because they will always be these rates. So for instance, length, 1 yard is 0.9 meters and 3 feet. So we know this 1 yard is 3 feet and 3 feet is 0.914 meters. And International System of Units, 1 meter is more than 1 yard. Okay? And of course, 1 yard and 1 meter are more than 1 feet because we said that 3 are 1 yard. Right? So this makes sense. 1/3 of a yard is a feet. That makes sense. Now, force in English or British system of units is pounds, English pound. In International System of Units is um, Newton, which is, that force is mass times acceleration. So it's in SI units is kilograms or grams per meter over second squared. Kilogram meter second squared. This is a Newton. And in British units, you have a dyne. So 1 pound is 4.45 newtons. This is, I almost never remember this, but this is one pound is 4.45 newtons. And 1 newton is 10,000 dynes. Sorry, not 10,000. 1 newton is 100,000 dynes. So 1 newton is much, much bigger than a dyne, to the point that we just said that 1 newton is 100,000 dynes. Okay, there's a very common sensor called dynamometer. Dynamometer, and this is used to measure the RPMs in a car, because you can use force to find torque, and then you can find torque knowing the radius of the shaft to know your RPMs. Okay, then mass, the British unit is slug, which is 14.6 kilograms, and the SI units is kilogram, which is 1,000 grams. So obviously a gram is 1,000 times less or fewer or lighter than 1 kilogram. But a slug is 14.6 kilograms or 14,600 grams. Energy, the unit of energy. So the English unit is feet per pound, and SI unit is joule, the last name like the scientist. And 1 feet pound is 1.356 joules. Okay. Now, what about temperature? We haven't talked about temperature or pressure, because pressure in British units is PSI, pound square inch, and SI is Pascal. Okay, so pound square inch and Pascal. 14.7 psi is 101 kilopascal. But what about temperature? I know the number right here because this is atmospheric pressure. So a sea level. So it's very easy to remember. 14.7 psi, 101 kilopascals, or 101,000 pascals. But what is temperature? So remember, the temperature is, of course, we can feel temperature by cold, and hot, but the definition of temperature is the amount of energy that particles have by bumping each other. So in fact, Kelvin, the unit Kelvin, starts at 0, telling you that whenever there's no energy whatsoever for energies to bounce against walls or against each other, that is true 0 Kelvin, which is zero energy within particles. So interestingly, the more common units of measurement that we use are Fahrenheit and Celsius. Celsius is SI and Fahrenheit is English. So you know that in Fahrenheit, 32 Fahrenheit is freezing temperature of water and 212 is boiling temperature of water. In Celsius, freezing temperature of water is 0 and 100 is boiling temperature of water. So almost anytime you see engineering applications, you use either air or water to tune your systems. Temperature is one of them. Temperature, you have water, which is 0 freezing and 100 boiling. So here water is liquid, below 0 is solid, after beyond 100 is a vapor. But Kelvin is 273 for when at 0 Celsius, and 373, so 273.15 plus 100 is 373.15. So this is 100 Celsius. This is at 0 Celsius. But 0 Kelvin is extremely cold, as you can see. So like 1 Kelvin is extremely cold because this is close to vacuum. This is approaching vacuum where there's no particles. So the formulas to compute Fahrenheit, Kelvin, and centigrades are, or Celsius are, if you have Celsius, you can compute Fahrenheit by 9/5 of your temperature in Celsius plus 32. That will give you your temperature in Celsius. If you have Fahrenheit, you want to convert to Celsius, is 5/9 of your temperature in Fahrenheit minus 32. That's your temperature in Fahrenheit. And Kelvin is 273.15 plus your temperature in Celsius. So we talked about this before, powers of 10. So if you have 10,000, that is 1 and then 1 0, 2, 3, 4 zeros, then this is 10 to the positive 4. And if you have 0 0.00001, that is a 1 with 1, 2, 3, 4, 5 until you see the dot, the decimal point. This is 5, so this is 10 to the negative 5, like so. When you have powers of 10, you can do the exponential rule of 10 to the n times 10 to the m is 10 to the n plus m. In other words, if you have 10 to the second power times 10 to the third power, this is 10 to the 2 plus 3 is 5. Okay, and then also 10 to the negative 2 is equal to 1 over 10 to the 2, or 1 over 100. Okay, and evidently, if you have 10 to the 2 over 10 to the 3, you can subtract, which is 10 to the 2 minus 3 equals 10 to the negative 1. Now, if you have a power raised to an exponent, then you multiply them. Not like this. When you have 10 to the something plus 10 to the something else, you can add them. When you have 10 to the something raised to a power, then you multiply them. So for instance, if you have 10 to the second power and all that raised to the third power, then this is 10 to the 2 times 3 is 6. Okay, so please review these concepts. Multiplication factors. So we already talked about this a little bit. So we said pico is 10 to the negative 12, but there's also femto, which is 10 to the negative 15, and atto, which is 10 to the negative 8. The positive range, we have kilo, 10 to the positive 3, mega, 10 to the positive 6, giga is 10 to the positive 9, tera is 10 to the positive 12, kind of like terabyte, peta is 10 to the positive 15, and exa is 10 to the positive 18. Beta 15 and xi is positive 18. Symbols, very important to remember the symbols from now on. So this right here, an equal with a line through it, is not equal to. So 3 is not equal to 4. Greater, very important. 3 is greater than 2. Much greater, 1,000 is much greater than 0.1. Less than, 5 is less than 6. Less than, much less than. So 5 is much less than infinity. Greater than or equal. So 5 is greater than equal the price of gas in, I don't know, 2030 or something. We can do these relationships mostly when you're creating a code as software. Less than equal is the same concept but reversed. Approximately equal. So I don't know. The weight the weight of planet Earth is approximately equal to 10 to the 24th kilograms or tons, I think, tons. An example. Sum, so this is when you have 1 plus 2 plus 3, you do sum of I to 3 when I starts from 1. Okay, so this is what 1, I is 1 plus I is 2 plus I is 3. This is sum. Absolute of, so this is the absolute magnitude of -3 is equal 3. Therefore, this is when you're proving a theorem, by definition, okay, by definition is, I don't know, the boiling water, I don't know, some example by definition. So by definition, we'll see a lot. By definition, the units of resistance are ohms, I guess. Ratio, A to B. Proportion, A to B to C to D. So A to B is to C is to D. All right. So all of these things are used for programming languages. So very common programming languages are formula translation, Fortran, C and C++, Python and JavaScript, etc. In this class, you can use MATLAB if you want to learn, or for some homeworks, it will be easier if you use Excel than the calculator, because then you can compute a bunch of rows and graph whatever you wanna do. So you can use Excel if you want. You can try to learn MATLAB, which if you're gonna go for science and engineering, you'll definitely use it again. You can even try to use Python. So whatever you wanna do. Now, in terms of software, we will use any of these things. You let me know what you wanna do. I will use definitely Multisim. So Multisim, you just have to create an account with your email. Hopefully you can use your college email, so it's easier to log in and free. Okay, but you can also use Autodesk, Fusion, AutoCAD. I will definitely use Tinkercad. So Tinkercad is another one that I will use a lot. Tinkercad.com, and I'll have videos on them using Tinkercad. But you can use Cadence if you want. Cadence is a very good one for creating software and circuits. So it's up to you. Review all the links and let me know which one you would like to use. I will use Multisim and Tinkercad. Thank you.